Okay guys, in this next video we are going to be looking at measurements as well as a discussion of the precision of measurements, and then we'll have a separate video here which mostly covers units. Okay, so let's take a look at this next section. We'll talk about what measurements are and the three essential parts of a measured quantity. And then we'll get into doing calculations in both this video and the next one. So a measurement is a type of comparison. So you're comparing some physical quantity that you're observing in nature against a known standard. And that known standard is what we call the unit. You can take length as an example. So suppose you were using a standard US ruler. It has both inches and centimeters listed on the sides, and so these are two different units. Okay, they both measure length, but they're not equivalent to one another. In fact, 1 inch is about 2.54 centimeters, and that's something that this relationship here is what we will call a conversion factor, and we'll be using a lot of conversion factors in chemistry. So the three parts of a unit, okay, so if you want, or the three parts of a physical measurement, if you want to report a measurement to someone, you need to specify the number of units for that quantity, so that's the magnitude of the quantity. You need to tell them what unit you are using, okay, otherwise it wouldn't do any good to tell them how many units you have if you don't tell them what units you're using. And then the third part, you want to give the person you're communicating with some estimation of the precision of the measurement. That is, how good of a measurement is it? And that's what we're going to talk about here in this next section. So we'll talk about uncertainty in measurements, and we'll define the quantity's accuracy and precision. And then we will go through the tools that we use, these significant figures. These are the tools for representing the precision of a quantity. So, precision and accuracy, they sound similar, and they both are used to characterize the quality of a measurement, but they're not quite the same thing. So suppose you're making repeated measurements of some quantity. The precision of your measurement is the closeness of all of those measured values to one another. So do you get the same value when you do repeated measurements? How close those repeated measurements are to one another is an estimation of the precision of the measurement. Accuracy refers to how close the measured value is to the true value of the physical quantity. Okay, so they sound similar, but they're slightly different. And then the two ideas are represented in these three diagrams here. So let's suppose that you are trying to locate someone with GPS. So we have a bird's eye view of the terrain, and the person with their phone is at the center of the bullseye. And the dots that you see, those represent the measured value of the person's location. So on the diagram on the left, we see that three measurements have been made, and they are all very close to one another, which means that the measurement is precise. Moreover, they are also very close to where the person is actually located. So we would say that these measurements are both accurate and precise. In this middle panel, we see that the three measurements are pretty close to one another, so they're precise. However, we see that there's a deviation from where the person is actually located. So we would say that these measurements are precise, but not necessarily very accurate. And then in this third case, we see that there's a large spread in the measured values for the location of the person, and also the measured values are very far from the true location of the person. So these measurements are neither accurate nor precise. There is no such thing as an exact measurement, so all measurements have some finite precision. There's always some uncertainty in the measurement. I should take that back. There are certain types of measurements, in particular counting measurements, which can be done precisely. So if you're counting in whole numbers, it is possible to get a precise count of something. So counting can sometimes be exact, which means that you're completely certain as to what the value of the measurement is. When you're talking about numbers, we'll be using imprecise numbers to represent most of our physical quantities. But then occasionally in some of our formulas that we will use, so different equations that we use, there will be exact numbers. And an exact number it's like a counting number. It's either an integer or it's a ratio of two integers, so a perfect fraction. These types of numbers are infinitely precise. Okay, and so we'll be doing calculations with both measured numbers, which have a finite precision, as well as calculations involving exact numbers. Here's an example of precision in a measurement that you might do in chemistry. So suppose that you're measuring the volume of a liquid with this graduated cylinder, and we want to report the volume of the liquid used. So clearly we can see that we have at least 21 milliliters of liquid, but not quite 22. Okay, so where we read the mark here is at the bottom of this meniscus, and so we want to estimate what decimal represents this line in the liquid volume relative to these two hash marks here on the side of the graduated cylinder. And so you would estimate that it's a little bit more than halfway past 21. So why don't we call it 21.6 milliliters? Okay, so this is how you would report. You would report the value of the volume. The 21 part is certain. You definitely have at least 21 milliliters, but then that 0.6, that's an estimate. Okay, there's no hash mark at 0.6, so I don't know that it's exactly 0.6, but I'm just using my best guess between the two hash marks that I do have. Okay, so the value here that we see tells us just that. It tells us that the 21 milliliters is certain. We definitely have 21 milliliters. And then the 0.6 milliliters portion of the number that's reported is uncertain. And a scientist would interpret this to mean that the value of the volume is probably accurate within a couple of tenths of a milliliter. So it could be plus 0.2 milliliters or it could be minus 0.2 milliliters. This 0.6 is uncertain, but I know that we have at least 21 milliliters. Okay, and so that's how you report the precision of a measurement. We will be doing calculations with measured quantities, and the rule is when you're doing calculations involving measurements, the precision of the calculated quantity cannot be better than the precision of the input measurements. Okay, so you can't calculate something that's going to be more precise than the measurements upon which the calculation is based. So we need some way of keeping track of precision in our calculations, and that's what significant figures are all about. They're a tool that we use to keep track of precision in calculated quantities involving measurements. So the significant digits within a number include all of the digits in the number that are certain, for example, the 21 portion of this number, plus one digit that is uncertain, which would be the 0.6 here in this example that we did previously. So that's what we want to be reporting in our calculated quantities now. So here are the rules for determining how many significant figures you have in a number. First, anytime there's a non-zero digit, those are all significant. Zeros are a little bit different. If you have a captive zero, that is one that is located between two non-zero digits, then those captive zeros are significant. Leading zeros are not significant. Trailing zeros, when you have a decimal point present, are significant, but trailing zeros when there's no decimal point present are somewhat ambiguous. Okay, and so we will use these rules here to evaluate the number of significant figures in these different numbers. So let's go through these examples. So in this part A, okay, we have several non-zero digits. Each of these are significant digits, and then we have one trailing zero when there's a decimal present. And so we are to interpret this zero as being significant. So in this number, we have a total of 5 significant digits. Okay? All of these digits are significant. In the next example, the 2 leading zeros are not significant, so neither of these are significant digits. However, the captive zero here, which is located between 2 non-zero digits, that one is significant. And because we have a decimal point present, we know that that trailing zero is significant. So right here, these are the significant digits in the number, and we've got 5 of them again. In part C, all 4 digits are significant. In part D, these 6 digits are significant. For part E, none of these leading zeros are significant. The significant digits are these last 3. In part F, all of these are significant. We have a decimal place, and so all of the trailing zeros are significant. So we've got 5 significant figures here. In part G, the captive zero is significant, the leading zero is not, and so we have 6 significant digits in part G. Part H is ambiguous, okay, and that's why I've included it here. There's no decimal place here, so we don't know how precise this number is. Is it precise down to the ones column? For example, is this significant or not? We don't know. Is it precise just to the tens column? We're not sure. Or is it only precise to the hundreds column? Again, it's not clear to us based upon just this number alone, because there's no decimal point present. So it's an ambiguous question. We use scientific notation as a tool to remove that ambiguity. Okay? So scientific notation is used to report the precision of very large and very small numbers. And so here's 2 examples. So suppose we have a very large number, okay, a 1 followed by 12 zeros, and suppose that this number is only significant to this decimal place, right here. Well, the way we would report that is we would write this number in this format here, which tells us that we have 2 significant figures, but then it's a very large number because it's multiplied by this 10 to the 12. Likewise, when you're working with very small numbers, so let's suppose that we have this very, very small fraction, and then this last zero is supposed to be significant. Well, it's very cumbersome to write this entire thing when you're talking about this small number. So what we do is we use scientific notation. We have a number here with 2 significant figures, and it's multiplied by a very small fraction, 10 to the minus 12 in this case. And so the format that we're looking at here, this is called scientific notation. So a number is represented by a number A, which is called the significand, and it has the appearance of having 1 digit to the left of the decimal place, and then it could have any number of digits after the decimal place, times 10 to some exponent, n, where n is an integer, positive or negative. When you're working with a calculator or on a computer, sometimes the scientific notation is represented by an e to the n, where this e stands for exponent. And so just be aware of that in some notations, the times 10 to the n is actually substituted by this en, or sometimes it's EEN. This graphic here shows a bunch of different powers of 10. So 10 to the 12th going down, 10 to the 9th, 10 to the 6th, 10 to the 5th, 4th, 3rd, down to 10 to the 0, which is just 1, and then starting the negative exponents, 10 to the minus 1, 1 over 10, 10 to the minus 2, 1 over 100, and so on, going all the way down to 10 to the minus 12. So these are the exact representations of these powers of 10, and then these are approximations. These are the decimal approximations to these exact fractions. So why are they approximate? Well, in order to exactly represent 1 divided by 10 in decimal form, I'd have to have an infinite number of zeros following this 1. And that would be very awkward, so of course I wouldn't write that. So I just wrote it as approximately 0.1. Well, in this example, we are to take decimal numbers and write them in scientific notation. So I just wanted to go through that process. And so let's start with the first number here, 843.4. And we are going to write this in scientific notation. Proper scientific notation has the significand with 1 digit to the left of the decimal place. Now notice that I've made this number smaller. So I need to multiply by a power of 10. That's going to make it bigger. So you're going to have a positive exponent in this case. And what should the exponent be? Well, how many places did you move the decimal? 2 places in this case. Just like that. So part B here, this time we have a small number. Let's write it in scientific notation. So we should have 1 digit to the left of the decimal place. And now we're going to multiply by a power of 10. What should the power of 10 be? Well, notice this is a small number, and I've written it as a larger number. So I need to multiply by a power of 10. That's going to make this as small as that. Okay, so I need to have a negative power. What should the power be? 1, 2, 3 decimal places, 10 to the minus 3. For part C, it's kind of silly. You really don't need to use scientific notation for this number, but if you were, you would write it as 10 to the 0, because 10 to the 0 is just 1. And anything multiplied by 1 is just the number back again. Same thing for part D. Nothing. We would just write it as 4.38 times 10 to the 0. For part E, we have a large number, so 4380. Let's write it in scientific notation. Got my 8 and 0 backwards. Let's write it like that. Notice that we took a large number and we wrote it as a smaller number. So we need to have, we need to multiply by a power of 10. That's going to make it larger, and that power of 10 should be 3 decimal places. For part F here, we have a small number. Let's see, there's three zeros there, 8. We would write this as 4.38. So we go from a small number to a larger number. We need to multiply by a power of 10. That's going to make this as small as that. And so we're going to have a negative exponent in that case. 1, 2, 3, 4. 10 to the minus 4. Okay, so this is converting decimals to scientific notation. We can also go the other way. So working the bottom exercises here. 6.39 times 10 to the minus 4. Okay, you basically want to move this decimal place to the left 4 places. For part B, we have 3.275 times 10 to the 2. We're going to move, since this is a positive power, we're going to move it to the right 2 places to make it bigger. For part C, we have a positive power, so we need to make the number larger, like that. And for part D, we have a negative power, and so that's going to make the number smaller. just like that. Okay, so that's converting scientific notation back to decimal. Next, we want to be able to do calculations in scientific notation, and later we'll also add to that doing calculations with significant figures. So on this slide, I have listed out different rules for manually combining numbers in scientific notation. So when you're adding and subtracting, you typically need to factor out a common exponent and then add or subtract the significans. When you're multiplying and dividing, it's a little bit easier. You need to combine the exponents according to these rules here, the multiplication and division rule for exponents, and then you just do the same thing to the significans. When you're working with powers and roots of numbers in scientific notation, whenever you take an exponent to a power, you need to multiply the exponents together. Whenever you take a root of an exponent, you need to take the power of the exponent and then divide by which root you're taking. And so on the next example, I've got just a number of problems to be practiced. And so let's go ahead and work out a few of these. And so I'm just going to do one of sort of each type here. And so parts A and B are basically the same. And so I'm just going to work out part A for us. Okay, so you've got 9.42 times 10 to the minus 2 plus 7.6 times 10 to the minus 3. Now, you do need to be able to just do that type of thing in your calculator. But it's also helpful if you can do it by hand if you need to. And so what I'm going to do is illustrate how you do it by hand. So in order to carry out this operation by hand, you need to get the 2 powers of 10 on an equal footing. And there's different ways of doing that. What I like to do is I like to change the number with the larger power, that's the 10 to the minus 2 in this case, and make it the same as the number with the smaller power. And so what I'm going to do is rewrite this number as 94.2 times 10 to the minus 3 plus 7.6 times 10 to the minus 3. So notice I made the power smaller, so I need to make the significand bigger, right, so that it's the same number. And now you can just combine the two significands, so 94.2 plus 7.6 gives us 101.8 times 10 to the minus 3. I guess I sort of skipped a step in the sense, let me go ahead and show you what I just did there explicitly. I factored out the 10 to the minus 3. Both numbers have 10 to the minus 3, so I factored them out. Then I can add these two numbers together. And then what I can do is I can make a final adjustment to give me the number in proper scientific notation. So I would want to write that as 1.018 times 10, and I've taken a larger number and made it smaller, so I need to make the power of 10 bigger. So I'm going to be adding back 2 powers of 10. So we might write that as 10 to the plus 2 times 10 to the minus 3. And then when you combine these powers of 10, you just add them together. And we would get minus 1. Let me show you how I enter scientific notation on my calculator. So for part B, I'll do part B via the calculator. You may have a different calculator, but what I wanted to point out is that usually there's a special button for doing powers of 10, and it's not the button that you think. So I see students using the anti-logarithm often to enter in scientific notation. That's not really what that button is for. Most calculators have either an EXP button or they'll have a double E button. And you may need to use your Shift key in order to find that double E button. Anyway, this is how you enter in scientific notation. 3.142 exponent minus 4 in this case. And then we'll go ahead and add in the next one, plus 2.8, go to scientific notation, minus 6, and that gives you the answer. So for part B, I got 3.17 times 10 to the minus 4 for the value. So take a look at your calculator and check to see what button you're using for scientific notation. I really don't recommend that you use the anti-logarithm button to enter in scientific notation. There's an EXP button on mine. Many calculators, it's a double E button, which is accessed by one of the Shift keys. I'm going to go ahead and do part C because it's a multiplication type problem. And so 6.3 times 10 to the 2 times 2.4 times 10 to the 5th. Okay, so we are multiplying these two numbers together. How you do that is you multiply the two significands. So 6.3 times 2.4 gives us 15.12, and then it's times 10 to the 2 times 10 to the 5th. And the way you combine these is you combine them by adding together the exponents, 10 to the 7th. And then we would make an adjustment for to get the number in proper scientific notation. And in the end, we'll learn that we would write that as 1.5 times 10 to the 8th. We'll learn about that soon. I did a little bit of rounding at the end. I'll leave part D as an exercise for you to try, both with your calculator and manually. And then I just wanted to point out part E, which is division. So we'll do 6.4 times 10 to the 2 divided by 2.0 times 10 to the 5th. So that would be 6.4 divided by 2.0 times 10 to the 2 divided by 10 to the 5th. And this is going to give us 3.2 for the significand. And then for the powers of 10, it's going to be 10 to the 2 minus 5. So we're going to wind up with 10 times 10 to the minus 3 as the answer there. I'll leave part F as an exercise for you. And then I'm going to work part G right over here. So here we have a power, 5.29 times 10 to the 2 to the power of 3. We can write this as 5.29 cubed times 10 to the 2 cubed. And so 5.29, I will use my my x cubed button here. So that gives me 148.035 and some change. And then to do the power of 10, just double check that. Yeah. 10 to the 2 to the third power, here we multiply the exponents. So it would be 10 to the 6th. Okay? And I'm going to write that as 1.48 times 10 to the 8th. Right? I'm putting it in proper scientific notation, and I've rounded to get rid of these insignificant decimals. For roots, it's similar, 2.32 times 10 to the 6th. You can write this as the square root of 2.32 times the square root of 10 to the 6th. In that case, you would divide the power by the root that you're taking. So this would be 10 to the 3rd. And then 2.32, take the square root, we would get 1.52 for that one. Okay, and so the ones that I haven't done for you, you would try on your own. You should also try these with your calculator. Make sure that you can use scientific notation with your calculator. That's an important skill. And let me know if you have any problems with your calculator via email, and we can set up a time where you can hopefully show me your calculator, and then I can help you decipher how to use it properly. Okay. Well, you'll notice I did a little bit of rounding in some of those problems, and that's something that you often need to do when you're working with measured quantities. You need to truncate the number so that you have the correct number of significant figures. And so in this next example, what we're doing is we're talking about the rules of rounding, and then I'll just give you a few quick examples of how to use these rules. So you usually need to round to some particular number of sig figs. So in the examples that we'll do, they want us to take all of these numbers and round them to 3 sig figs. So they want us to round to this decimal place right here. This would be the first uncertain digit. And how you decide how to round is you look at the next uncertain digit, the so-called second uncertain digit in these rules. And depending on what digit this number is, you will either round up or round down. And here are the rules. If the second uncertain digit is greater than 5, then you round up. If the second uncertain digit is less than 5, then you round down. And then here's the more complicated one. If the second uncertain digit is 5, then you round up if you're rounding to an even digit, or you round down if that's how you get the even digit. And I'll show you what I mean in these examples. So let's do these examples here. So part A, right? Okay, we want to round to that column right here, to the hundredths column. And so we look at the second uncertain digit. It's a 4. That's not greater than 5. It's less than 5. So we will round that down. We will write the number as 1.21. For part B, we want to round to here. And again, we see that the second uncertain digit is less than 5. And so we will round down 5.65. For part C, here the second uncertain digit is larger than 5, and so we will round up 2.55. For part D, this is a fun one. The second uncertain digit is greater than 5, and so we would round this one up to 1.50. In parts E and F, the second uncertain digit is 5. In part E, we see that if we round up, then the 1 would become a 2, which is an even number, and so we would round up in that case to 1.22. However, for part F, we see that the uncertain digit is already even. The second uncertain digit is a 5. In this case, we would round down to keep that digit even. This rule is meant to compensate for round-off errors. Okay? And so that's how you round to a specific number of sig figs. And we will be doing that in lots of our calculations, so we'll get more practice with it as we go. In this next topic here, we're going to discuss how to do significant figures in our calculations. And again, the main idea is that your calculated results involving measured quantities cannot be more precise than the original measurements. And so you need to keep track of significant figures in your calculations, and we do that using these rules here. And so I'll just state the rules very quickly, and then we'll get to the examples. When you're multiplying and dividing numbers, okay, so you've got two numbers that you're multiplying or dividing. You need to count up the number of sig figs in each of the numbers, and then the result of the multiplication or division should have the fewer number of sig figs. When you're adding and subtracting, it's a little different. Instead of counting sig figs, what you actually count are decimal places. And the rule is that the result of adding and subtracting should have the fewer number of decimal places. And you'll see what I mean in a second. If you're working with exact numbers in your calculations, you ignore the sig figs for the exact numbers, and that's because exact numbers have infinite precision. And we'll do an example of that as well. So here's some examples for us to try. Okay, so for part A, we've got 3.38 minus 3.01. And so we are adding and subtracting. Okay, so we're not really interested in counting the sig figs per se. What we are interested in doing is counting the decimal places. And so we see that both of these numbers are significant to the hundredths column. And so we'll take our 3.38 minus 3.01. Calculator tells us that it's 0.37. They both have the same number of decimal places, and so we leave this as 0.37. Okay. Let's do another one, part B. Here the two numbers have different numbers of decimal places. Notice that this one is precise to the hundredths column, whereas this one is precise to the thousandths column. So this one has more precision than that number. Right? It's precise to more decimal places, whereas this one's only precise to the hundredths column. So what you need to do is look at the two numbers and see which one has the fewer number of decimal places. It's this one. And the result, let me go ahead and get what the calculator says the result is. It says it's 5.012. The result cannot be more precise than that number, okay? Because this number is limiting the precision of the result. And so we need to round this number down. 5.01 is the correct answer. For part C, it's similar. 8.91 plus 6.435. Okay. This one's precise to the hundredths, even though this one's precise to the thousandths. Our result can be no more precise than to the hundredths column. And so we get 15.345 out of this. It's only precise to the hundredths column. In this case, the second uncertain digit is a 5, but the first uncertain digit is already even, so we are going to round down in this case. And so that's our result. Now part D is a fun one. Okay, so here you've got 6.81 plus this very, very small. I can't even count how many. We've got four zeros there. 1, 2, 3, 4, 2, 5, 5. Okay. Notice this is precise to the hundredths, and the hundredths here is 0. Now this number is more precise than that in the sense that there's more decimal places covered. However, these are completely insignificant relative to that 0.01 in this 6.81 number. Okay, so this is totally insignificant compared to that. And so the result is just 6.81. I call this the drop in the bucket, right? This is a drop in the bucket compared to that number. And so we just neglect it. Next, we're doing multiplication and division. Okay, so let me copy the problem down here. 2.568 times 5.8 divided by 4.186. Here, we're doing multiplication, and it's a different rule. So instead of looking at decimal places, we look at the number of sig figs. And this number has 4 sig figs, this one has 2, this one has 4. The rule is that the product, or whatever the division is, it should have the same number of sig figs as the number with the fewest sig figs in the input. So I'm going to work out the answer here in my calculator. And we'll look at all of the digits coming out of the calculator. 3, 4, 7, 9, etc. And a lot of those are not precise. In fact, we need to have only 2 significant figures in our number, and so that should be to there. And so we would round that down to 62 point. We can do another one here. So 5.61 times 7.891 divided by 9.1. Let's go ahead and run that through our calculator. Right, this is 3 significant figures, there's 4 there and only 2 there, so again we should have only 2 sig figs. This one we're going to round up to 4.9. In the next 2 problems, we are actually mixing addition and subtraction. So here you need to be a little bit more careful about how you do them. You need to just kind of go slow and take it sort of step by step. So I'm going to go ahead and copy this problem down. And you need to follow the mathematical rules of operation, okay, which tells you that you need to do what's inside the parentheses first. So we're going to do that calculation first. I guess we've already done it. 0.37, and it's precise to that hundredths column. Now we would want to work out the multiplication. So we would take the 0.37 times the 58.16, and that's giving us that number. And what you want to keep in mind now is what should be the precision of this intermediate number. Right? We've got 2 significant figures here and 4 there. So I'm going to underline this digit here to let me know that this number is only precise to the ones column. Now I'm going to go ahead and carry out the operation here. And I get minus 17.3392. And I know that now that I'm subtracting, I need to look at the number that has the fewest number of decimal places, and that would be the 21 in this case. And so again, this number should only be precise to there, and so I need to round it down. So that's the correct result. On your first assessment, you're going to be given little mathematical expressions like this, and you're going to be asked to calculate the answer using the correct number of sig figs. And the choices that you'll have, one of them will be the correct one, and then the other one will be like minus 17.3392, another choice will be 17.33, another choice will be minus 17.3. So which of the following is the correct one? They all look the same, they all came out of your calculator, but you need to know which one is the correct one. Okay? And then in this case, it's that one. Okay? So you want to get some practice working these out to make sure that you can get the correct number of significant figures when you are adding, multiplying, subtracting, and dividing measured quantities. Here's another example problem. This one involves an exact number. I'll go ahead and use this part of the page. So here we count that there are 9 coins in a bottle, and the mass of that type of coin is 3 grams. We're being asked to calculate what is the total mass of all the coins in the bottle. Okay, well, you counted it up. There's 9 coins, and then each coin weighs 3.0 grams. Okay, you do the calculation, right? I'll even use my calculator, times 3.0. It spits out 27 points. So that's what you get from your calculator. Now the question is, how many sig figs should the answer have? Should it have 2 sig figs or should it have just 1? If you follow the rules too closely, you might think it should only have 1 sig fig, and you'd round that up to, to 3.0 times 10 to the 10 to the 1. But that's incorrect. This is an exact number because you counted it exactly. So this number has an infinite number of sig figs. And so really, reporting the number as 27 is the correct thing to do in this case. So just keep in mind, when you're working with exact numbers, you don't have to worry about the significant figures in the exact number because there's an infinite number of them. Okay, well, I think that's it for this video. On the next video, we will start talking about units. So I'm going to go ahead and stop this here.